Okay, so today this is the last portion of our coverage of numerical integration, and then the rest of the semester will be about finding solutions of nonlinear equations, group finding methods. Here we have really my favorite integration technique, and not just because it plays a key role in my research, but it's just so effective. And some very nice properties. Okay, Gauss Quadrature. So, when I talked about early on regarding integration, interpolatory quadrature rules. So in other words, quadrature rules in which the integrand f of x is approximated by a polynomial. We have a concept of degree of accuracy. So the highest degree polynomial that's guaranteed to be integrated exactly by the quadrature rule. Now, I gave you some information about degree back when I first introduced the concept, that if you have a quadrature rule n nodes, that's interpolatory, then because f of x approximated by an interpolated polynomial that passes through n points will have degree n minus 1. And then, so that polynomial will be integrated exactly because that's the definition of the quadrature rule. So any n node rule has a degree at least n minus 1. Degree can be higher, like Simpson's rule. We have 3 nodes and the degree is 3. So what we want to look at now is how high can a degree possibly get? What if we seek to maximize the degree of accuracy? So for a given number of nodes, we want to be able to integrate exactly polynomials as high degree as possible. And it turns out it's not so difficult to answer that question as to the highest possible degree, because if we have a general quadrature rule, we have 2n parameters. We have n nodes and n weights. So that suggests that it's possible to integrate polynomials of degree up to 2n minus 1 exactly, because a polynomial of degree 2n minus 1 has 2n coefficients. So what I can do is I could put in for f of x powers of x, x to the 0, x to the 1, x squared, and so forth, and require the quadrature rule to match the exact values of the integrals of those powers of x. So I can set up a system of 2n equations in 2n unknowns, where the unknowns are the nodes and the weights. And that is what is called direct construction. So here I have my 2n equations. The right-hand side is the exact integral of x to the j, and then the left side is the quadrature rule with unknown nodes and weights applied to x to the j. So because we have 2n unknowns, we can balance it out with 2n equations. So now what we can do is try to solve this system of equations for the n nodes and the n weights. And then we would have a quadrature rule that has some maximum possible degree. Now it seems like a simple enough idea, except for one big problem. This system of equations is nonlinear, because you have your unknowns, half of your unknowns, your nodes, being raised to powers. Also they're multiplied by the weight. So all these equations are nonlinear. And nonlinear equations are generally extremely difficult to solve. So what I do is go ahead and assign you one of them. In the case of n equals 2, 2 nodes, 2 weights, so you have 4 unknowns total. That equation can be solved, I swear. So I signed that for homework.
I just love the way you wrote it. So you get to do it for your homework.
Yay!
Yay!
All right. Okay. So, but in general, that's not a good approach to finding the nodes of weight. So we'd like to see if we can find something more effective. Fortunately, we can. But it involves a rather unusual concept that I'll introduce now called orthogonal polynomials. So I'm going to recall something that you would have learned about in calculus. So here anyway, Cal 3. That if you have two vectors, okay, I should be precise about what kinds of vectors. Oops, something was wrong here. Oh, okay, looks like I need to put in the right LaTeX package. Okay, got it. All right, so if you have two vectors in R3, then we can say that they're orthogonal if their dot product is 0. And what's a dot product? You multiply corresponding components of the two vectors, and then you add all those up. So now we have a natural generalization to an inner product of, or the dot product of functions. So we say two functions are orthogonal if the integral of their product, whoops, totally forgot the most important part, equals 0. I wrote these notes a couple years ago. I'm not sure what I was thinking back then. Okay. So there was a natural analog between this operation and this one. Like I said here, we multiply corresponding components and add them up. Well, what's happening here? You're multiplying values of f and g at corresponding x's, or that same x, so multiplying corresponding values of f and g, and adding in the sense of we're computing a Riemann sum, and then taking the limit of Riemann sum as the number of rectangles goes to infinity. So you can think of this in similar operation as this inner product with just with infinitely many terms. So now this you know of as the dot product of vectors. Here this is an inner product. A dot product is an example of an inner product. So inner product refers to a very general operation that has certain essential properties. So here are just two examples of that. Like for example, it's bilinear. For real value functions, the inner product is commutative, etc. Okay. So now that I have a way of describing functions being orthogonal to each other, by virtue of your inner product being 0, I can describe a sequence of orthogonal polynomials, so Q0, Q1, etc., where the subscript is the degree. So Q0 is a constant function, Q1 is a linear function, Q2 is a quadratic, and so on. And here are their pairwise inner products. So the inner product of each Qi with Qj is 0 if I is not equal to j, and 1 otherwise. So you can think of these polynomials as being like unit vectors in the sense of this inner product. So when you take the inner product of a vector with itself, that is its norm squared. So what I'm saying is that the norm of these, in that sense, is 1. Okay. So here are some well-known orthogonal polynomials. We have the Legendre polynomials. So Legendre polynomials are orthogonal on the interval -1 to 1. So here, a and b, a would be -1 and b would be 1. And here are Legendre polynomials. The first one is 1, then we have x. And then here we have a 3-term recurrence relation that describes each subsequent Legendre polynomial in terms of the previous 2. All right. Now, you may recall that there's another family of polynomials we saw some time ago that also satisfy the 3-term recurrence relation. Chebyshev polynomials. They are also orthogonal, but in a different sense. Still in the interval -1 to 1, but here, when you multiply them, you also have to include this weight function. So it's a different inner product than this one right here, because this one does not feature a weight function. So championship polynomials are orthogonal with respect to this weight function, 1 minus x squared to the minus 1 half. Which is interesting because this function is undefined at the endpoints of the interval, but it's defined everywhere inside. Notice also, I want to point out, the Legendre polynomials are orthogonal in the sense that inner product of Li with each Lj is 0 if I is not equal to j. But the inner product of each one of itself is not equal to 1, so they are not normalized. But we can still use them for what we need here for a quadrature. Right. And there are many other families of orthogonal polynomials, but these are two that are of primary interest to us. Okay. So what do we do with these orthogonal polynomials once we have them? We can use them to find the nodes for a quadrature rule of maximum degree. So what I'm going to do here is I'm going to assume that f of x is a polynomial of degree at both 2 and minus 1. So it has a degree that we should be able to handle by integrating exactly with our quadrature rule. So that's what we want. That we have this polynomial, a high degree polynomial, its integral is equal to what you get from a quadrature rule. But the quadrature rule is the exact integral of this interpolating polynomial of degree n minus 1. So just like other interpolatory quadratures, this polynomial agrees with f at n points, the n nodes, which at this point are unspecified. And this is how general interpolatory quadrature works. That a quadrature rule is equivalent to integrating the interpolating polynomial exactly. The difference is we want this to agree with the true integral of f. So no error in this case. So what is the error? So that we can make sure it's 0. Okay. So the error is the integral of the interpolation error. So f minus the interpolant. The key is now f is a polynomial itself. So this is a polynomial degree of 2n minus 1. This is degree n minus 1. So the error has degree at both 2n minus 1. Now, these two polynomials agree at these points. In other words, at these points, the difference is 0. And since this is a polynomial that's equal to 0 at these points due to these matching, this polynomial must have these factors in it. X minus x1, x minus x2, x minus xn. So we have a partial factorization of this error polynomial. And then what's left over is we have some polynomial here that's of degree at most n minus 1. That's what the subscript is for. This actually gives us some guidance on how to choose the nodes for a quadrature rule to maximize its degree of accuracy. What we do is we choose them to be the roots of this polynomial, Qn of x, polynomial degree n that is orthogonal to all prior orthogonal polynomials. But by the linearity of the inner product, if Qn is orthogonal to all these orthogonal polynomials of lesser degree, it's actually orthogonal to all polynomials of lesser degree. Because it would be orthogonal to any linear combination of these. Now, because Qn has these points as roots, I know it has this form. It's some scaling constant times these factors. Now, what's interesting is, and unfortunately, I don't have time to go into it today, but it can be proved, and these are actually problems in the book that I did not assign, that the roots of these orthogonal polynomials are real, they are distinct, and they fall within the interval AB. So that's quite unusual. Normally, if you have a polynomial degree n, you know it has n roots, but the roots might repeat, or they might be complex, and they can fall anywhere. But here we know they have to fall within AB and be real and distinct. And it's because of this property of orthogonal polynomials. So, what that means is, from this equation here, I can say that this product of linear factors, so that this right here, is equal to Qn over beta n. So the error that I have here, and remember this is equal to the integral of Pn minus 1, is equal to the inner product of Qn over beta n with Rn minus 1. And Qn is of degree n. This has to be of lesser degree because it has degree at most n minus 1. Because Qn is orthogonal to all polynomials of lesser degree, this inner product must be 0. Therefore, the error is 0. Therefore, this quadrature rule produces the exact integral of f. So what we've shown here is that this quadrature rule with these nodes is exact for all polynomials of degree up to 2n minus 1. Questions about what happened here? So, when the nodes are chosen in this manner, then that's called a Gauss Quadrature Rule. Now, the weights are chosen the same way as in interpolatory quadrature in general, where you take the Lagrange polynomials for your nodes and you integrate them on AB, and those are the weights. Now, what to keep in mind though is that if your interval is minus 1 to 1, your orthogonal polynomials are Gaussian polynomials. So what you want are the roots of a Gaussian polynomial degree n. Now, if your interval is not minus 1 to 1, there's no need to generate some other sequence of orthogonal polynomials. All you need to do is take your, the x's are the Gauss quadrature nodes for minus 1 to 1, the roots of a Gaussian polynomial. All you got to do is scale and shift those nodes from minus 1 to 1 to the interval AB that you're working with. And voila, there's your Gauss quadrature nodes. I mentioned here that for certain values of n, you can look up Gauss quadrature nodes. So Gauss quadrature nodes are published in many places, to many decimal places, certainly not the Kendall-Brownell error. And so, for example, if you Google Gauss quadrature and get to the Wikipedia page, you'll find on that page tables of nodes and weights for certain values of n. I mean, smaller values of n, sure, but and those can be quite effective. Now, the weights, as I mentioned earlier, this is a Gauss quadrature rule is an interpolatory quadrature rule. So the weights are the integrals of Lagrange polynomials corresponding to your n nodes. But what's unusual is they're also equal to the integral of the Lagrange polynomials squared. Now, first of all, why does this matter? Because if we know that the weights come from the integral of a non-negative function, so Lagrange polynomial squared, that tells us that the weights are strictly positive. That's very important. I've mentioned before that if you have a quadrature rule of negative weights, it's not going to be very accurate. We'd like to have positive weights. So now we see that for a Gauss Quadrature rule, that can be guaranteed. And because the weights are known to be positive for any n-node Gauss Quadrature rule, no matter what n is, unlike Newton-Cotes rules, where if a number of nodes n gets high enough, you're going to have at least one negative weight. But here the weights are always positive, so that tells it can be proven as n goes to infinity, your Gauss Quadrature approximate integral will converge to the exact value of the integral. Now, you can look up weights along with nodes for the interval -1 to 1, corresponding to Orthogonal Polynomials. If you're on a different interval AB, no problem. Take your weights for -1 to 1, and you just scale them by b minus a over 2. So again, you're doing a mapping from an interval -1 to 1 to AB. Here you only have to take into account the sizes of the intervals, whereas for the nodes, you have to do a scaling and shifting. Okay. I think I'll take a break at this point. Pause the recording. Okay. Are any questions up to this point? Now, in case anyone watching finds it really odd that this could even be true, I'm just going to go ahead and prove it. Again, it's certainly not true in general, but the integral of a function being equal to the integral of its square. It is true in this case because of properties of orthogonal polynomials. So, okay. So if we take a look at the integral of the difference of Lagrange polynomial and its own square, okay. We want this to be, we want to show that this whole integral is equal to 0, so that would show that these two are equal. Now, what we need to note about the integrand so here we have a Lagrange polynomial, it's squared, also a polynomial. So what's the degree of a whole thing? Yeah. 2n minus 2. And that's less than 2 minus 1, so it can be integrated exactly. By the Gauss Quadrature rule. So now I can say that this is equal to sum of the integrand evaluated at each point. Oh, I need to be careful here. I need to use a different letter, J. The integrand evaluated at xj minus that squared. Okay. Times the weight wj. All right, so because this is low enough degree, this is exact. So now we need to figure out what this is. Now, so we consider two cases to keep in mind the properties of Lagrange polynomials. J not equal to I, and j equal to I. So when j is not equal to I, what's this equal to? It's 0, because Lagrange polynomial number I, yes, making email also saying 0. Lagrange polynomial number I evaluated at xj is 0 when I is not equal to j. So this whole expression in square brackets is 0 for I not equal to j. Okay. What about when I equals j? 1. Thank you, Walker, for
The only other option is how to go with it.
That's true. If I do get an email. Yeah, so now we have 1 minus 1 squared, 0. So this is 0 at all the nodes. So it's 0. It always bothers me that when I'm showing that some expression turns out to be equal to 0, there's always a little bit of excitement there. And I want to say, equals 0 and put an exclamation point, which will make everything wrong. Okay, so that's how you can see that in this case, it does really work out that way. So you can use either expression for the weights. It says in this case, this shows that they're positive. And that's what we really get out of that. Okay, to give you an idea as to how effective Gauss Quadrature rules can be, here's an example. The integral is Gaussian function from 0 to 1. So I want to evaluate this integral, or approximate this integral, with 8 digits of accuracy. So first I can try the composite trapezoidal rule. Now, I mentioned before, composite trapezoidal rule is a great rule for periodic functions, but for a function like this, not so great. It takes a lot of function evaluations to get that much accuracy. So let's try something else. Composite Simpson's rule, a whole lot better with its fourth order accuracy. Okay, well, why do we need any better than that? Well, we can do a lot better. So a Gauss Quadrature rule, 5. So now, it's not always the case that it's this much better. I mean, quadrature rules are different when it's different situations, but Gauss Quadrature rules are generally quite powerful, and that's why generally numerical integration software uses Gauss Quadrature or some variant of it. Now,
always, either Gauss or Euler that we use.
What?
As always, Gauss or Euler wins.
Yeah, I guess so. Yeah. So as for the error in Gauss Quadrature, because we've seen error formulas for other quadrature rules, like Newton-Cotes rules, or composite rules. It's a rather interesting case of Gauss rules, because normally, this is an interpolatory quadrature rule. So normally you would use this for the error. You have you're approximating f by interpolating polynomial. You're interpolating at the nodes. So then you integrate the interpolation error, and that's your quadrature error. But we actually don't do that in this case. And the reason why is this interpolation error would involve the nth derivative of f. But this rule is exact for polynomials up to degree 2n minus 1. So such an error formula would not reflect that. So what we do instead is actually use Hermite interpolation rather than Lagrange interpolation. So the error is the Hermite interpolation error. Now, what's kind of strange here to use this is when we saw Hermite interpolation some time ago, we can write the Hermite interpolating polynomial in terms of values of f of x times certain polynomials, that are like Lagrange polynomials, plus values of f prime times certain other polynomials. Okay, actually, this is a bit too brief of a summary, so I'm going to flip over to the book and show you there. Okay. Oh, something went wrong. Okay. So to refresh your memory about Hermite interpolation. So Hermite interpolation is meant to agree with f at the nodes, and the derivative is matched at the nodes. And here is the form of a Hermite polynomial that I mentioned a little while ago. So you have values of f times polynomials plus values of f prime times certain other polynomials that are used to make sure that these constraints are all satisfied. So this seems like an odd choice because here we have these f prime terms, and we don't want those anywhere near our quadrature rule. But here's what happens. Because because my error comes from the exact integral minus this integral. So, by linearity, I have a sum of f values times these integrals of these polynomials plus the sum of values of f prime at the nodes times the integrals of these polynomials. And these polynomials were derived some time ago, back when I covered section 7.5. So, what's interesting is the integrals of these polynomials, the k's, turn out to be 0. Meanwhile, the integrals of these polynomials, the h's, turn out to be this. And we saw what this is before. Those are the quadrature weights. So the integral of the Hermite interpolating polynomial turns out to be exactly the Gauss Quadrature rule. So because this part goes away completely, then we can use this for error analysis. So this is one of the other problems in this section that I assigned. I did not assign this one. I assigned this one. That what you can do is, okay, I should flip back to my notes. Dang, I should have just shared the whole screen. Okay. Okay. Go back to my notes. Okay, so here's the error. And so now we know that the integral of this is the quadrature rule. But now we have a formula for this. This comes from Theorem 751, the error in Hermite interpolation. So as with other interpolatory quadrature rules, the error in the integral is the integral of the error, but you have to pick the correct error. So whereas with other interpolatory quadrature rules, you would use a Lagrange interpolating polynomial here. In the case of Gauss Quadrature, you use the Hermite polynomial, and that will give you what you expect in terms of the degree of accuracy that you know the Gauss Quadrature rules have. So this error formula from using this starting point is what you'll work out in one of the problems. One thing that'll play a role is a theorem that I mentioned recently, the weighted mean value theorem for integrals. That'll be helpful to you. All right. All right. Now, in general, the f prime terms when you integrate them will not go away. It's only because we have Gaussian nodes that come from a roots of an orthogonal polynomial. That's why these strange things happen. How we can use the Hermite interpolant here, how the weights can be the integrals of Lagrange polynomials and their squares. All fall out from orthogonality. All right. This is the end for numerical integration. We have time for any questions about this or homework. All right, nothing new in the chat. So the problems from this section, this one using direct construction, find the quadrature rule in the interval -1 to 1, solve for 2 nodes, 2 weights. By solving a system like this for a case of n equal 2, where this is given by this integral here. So you set up this system and then engage in a lot of algebraic hijinks to solve it.
I have one question.
Yep.
I mean, it doesn't have to be this chapter, right?
No,
Okay. 9.1.6. Just, yeah. I'm in the process of working on it. I don't know where it's going necessarily, but when you say use Taylor expansions and Lagrange polynomials, is this to get one result or like use them both separately to show?
use them separately, but the resulting approximation will be the same.
Okay, but like, so we're doing it first with the Taylor expansions then. Okay, that's what I was gathering from doing it, but I just wanted to double check. Okay. Thank you.
And then the last part of the question is the order of accuracy error formula. You can have an easier time using Taylor expansion to get the error formula.
Okay.
More questions about anything? And I once again have a pretty good sized grading backlog, which I will eat into on the weekend. Screw my lights just get brighter all of a sudden. This example is going to talk about how you have a table of nodes and weights for Gauss Quadrature, in this case for 5 nodes. Actually, yeah, here's the nodes and weights for the interval -1 to 1. come from Quadrature polynomials. And then for this example, I wanted nodes and weights for interval 0, 1. So then I adjusted them here. And if you were to compare, you would find that the weights here in this column are half of the weights from the other table, because the first set of nodes and weights comes from the interval -1 to 1, but now we're in the interval 0 to 1, that's half the size. You can also see that the nodes are, actually it's easier to see in this case, the nodes are symmetric around 0 in the case of the interval -1 to 1. So they're symmetric around the center of the interval. And they're not uniformly spaced, because uniformly spaced would mean a Newton-Coast rule, which this definitely is not. I think I had earlier. Oh, okay. Here's the Wikipedia page for Gauss Quadrature that shows. Here we have exact formulas for the nodes and weights for 1, 2, 3, 4, and 5 nodes. But in other sources, you can find tables for larger values of n. That were worked out long ago. That must have been a real pain back then.
So now you have to do it for homework.
Okay. All right. Last call for any questions. Okay.